Welcome to This Explainer. Today we're stepping into the fascinating world of petroleum engineering, but we're going to look at it through a kind of different lens. We're literally going to treat the massive, heavy-duty oil well exactly like a human patient. Over the next few minutes, we're moving from diagnosing the root disease that plagues these engineering marvels all the way to executing the precise, heavy machinery surgery required to save them. Let's get into it.
So here's the multi-million-dollar question. Why does an oil well, which has been pumping away perfectly fine, suddenly just stop producing? I mean, think of it exactly like a patient experiencing a severe cardiovascular blockage. The infrastructure is there, the heart, or, well, in this case, the reservoir pressure, is pumping, but the flow is completely choked off. We need to find out why.
Okay, let's dive into this. When engineers look at a cross-section of the wellbore, they identify 4 distinct zones of damage. It's like a geological bullseye. Zone 1 is the external cake. That's a crust of solids plastered right onto the well walls. Moving deeper, we hit Zone 2, the internal cake, where fine particles have actually penetrated the rock's pores. Then there's Zone 3, the invaded zone, saturated by drilling fluids that have leaked out. And finally, way out in Zone 4, we reach the virgin zone. That's where the natural permeability of the rock remains perfectly healthy and unaffected. To cure our patient, we're going to follow a strict protocol today. 1. Identify the well damage. 2. Decode the pseudoskin effect. 3. Run lab analyses and tests. 4. Perform a coiled tubing intervention. And 5. Deploy the heavy-duty snubbing technique. All right, let's start with Chapter 1, well damage. This is where we uncover the actual root causes of our well's underlying illness.
By definition, well damage refers to any mineral or organic incrustations that alter the natural permeability of the reservoir or plug the perforations in the production tubing. Whether it's just a partial blockage or a complete absolute seal, these deposits effectively choke the critical area immediately surrounding the well. They stop the hydrocarbons from flowing to the surface. And, in this industry, a choked well literally means millions of dollars in lost production. So how exactly does a well get sick in the first place? Well, the ailments are surprisingly diverse. You could have mud filtrate invasion from the drilling process itself. Sometimes incompatible drilling fluids mix with reservoir oil to create these thick, nasty emulsions or sludges. Other times, just the introduction of water causes the natural clays in the earth to swell up and block the pores. Oh, and we absolutely can't forget organic asphaltene deposits. Those are heavy, tar-like substances that precipitate out of the oil when there's a sudden drop in pressure or temperature. Now that we know the diseases, we've got to measure them. That brings us to Section 2, decoding the pseudo-skin effect. Think of this as the critical blood work phase of our diagnosis. Now, what's really interesting here is the math. It totally demystifies a highly complex concept used by engineers. They use something called the skin effect to calculate exactly how much production is being restricted. But total skin isn't just one thing. It's actually a sum of many variables. There's SD, which is the actual physical damage or blockage we just talked about. But there's also S-inc, caused by the angle or inclination of the well, S-perf, related to how the well was perforated with explosives, and even S-frac, which accounts for hydraulic fracturing. By isolating these, engineers can figure out if the well is truly sick with deposits or if it's actually just a geometric issue. We have our symptoms and our math, but a good doctor never cuts without confirming. And that leads us straight into Section 3, laboratory analyses and tests. Before injecting any treatments down a multi-million-dollar well, engineers run a rigorous battery of lab tests on core samples and fluids. We can group these into 3 main diagnostic goals. First, chemical and solubility tests figure out exactly what kind of blockage we're dealing with. Second, petrographic and sedimentological studies look closely at the rock's structure and porosity. And finally, and honestly, perhaps most importantly, fluid and acid compatibility analysis. This ensures that the chemical medicine we plan to pump down the well won't accidentally react with the native oil to create an even worse blockage. Imagine making the patient sicker? Definitely not what we want. So the lab work is in, the diagnosis is totally confirmed, and it is time for surgery. Let's look at our first major procedure in Section 4, coiled tubing intervention. Coiled tubing, or CT for short, is an absolute marvel of modern engineering. I mean, picture this, a continuous, seamless, flexible metal tube, anywhere from 1 to 4.5 inches in diameter. Now imagine wrapping that solid steel tube around a massive spool, kind of like fishing line. The best part? This continuous pipe can be unspooled and pushed straight into a highly pressurized well without ever having to halt oil production. And, incredibly, these flexible steel tubes can reach up to 9,000 meters in length. That is wild!
The operational sequence is just a beautiful display of mechanics. Step 1, the tube is unrolled from that giant storage reel. Step 2, it passes up and over a curved guide called the gooseneck to straighten it out. Step 3, a heavy-duty injector head literally shoves the steel pipe down into the high-pressure wellbore. Step 4, treatment fluids or acids are pumped down the tube to dissolve our well's blockage. And finally, Step 5, the tube is simply pulled back out and rolled right back onto the reel.
And this brilliantly illustrates that whole process. Starting from the bottom left, you can see the massive CT reel mounted right on the truck. The steel tubing goes up over the curved gooseneck at the top, straight down into the injector head, and forces its way through the blowout preventer, or the BOP, and the wellhead directly into the earth. It's a completely sealed, continuous loop of absolute surgical precision. But just like any surgical procedure, we have to weigh the risks and benefits here. On the pro side, coil tubing is incredibly fast to deploy. It's very cost-effective, it works wonderfully in horizontal wells, and crucially, you don't have to kill the well's production to do it. But the cons? Well, bending solid steel onto a spool causes mechanical fatigue over time. The pipe can literally wear out and snap. Plus, pushing a thin, flexible tube into a high-pressure hole creates a pretty severe risk of the pipe buckling under compression, which puts a hard limit on how deep you can actually go. So what happens when the well is too deep, or the blockage is too severe for our flexible tubing? We need a heavier option. Let's move to our final section, the snubbing technique. Now, you might hear the word snubbing and instantly think of a bad date ignoring you to stare at their phone. But in the petroleum world, snubbing is a whole lot more hardcore. Invented way back in 1928 in Louisiana, it actually means physically forcing rigid, threaded drill pipes into a live, highly pressurized well without having to inject heavy mud to kill the well's pressure first. Just take a look at the sheer scale of a snubbing setup here. Unlike the relatively low-profile coiled tubing truck we talked about, a snubbing unit requires building a massive, vertical structure right directly over the wellhead. You can see the towering telescoping mast, the heavy support cranes, and those complex staging baskets high up in the air. Make no mistake, this is heavy-duty surgery. Because the well is highly pressurized, it constantly wants to just spit the pipe back out, right? To overcome this, snubbing uses multi-cylinder hydraulic jacks that operate in massive 10-foot strokes, literally forcing the pipe down. It uses a tag team of traveling and stationary slips, which are essentially giant hydraulic jaws, to grab the pipe, push it down, hold it in place, and then reach up to grab the very next section. And all of this happens safely inside a complex blowout preventer stack to ensure the well doesn't erupt. So the crucial point is understanding when an engineer chooses which tool. Let's do a quick showdown. Coil tubing versus snubbing. Coil tubing is like the quick, minimally invasive arthroscopic surgery, using continuous, flexible tubes for fast, relatively light jobs. Snubbing, on the other hand, is the open heart surgery. It uses rigid, threaded pipes. It definitely takes longer because you have to screw every single pipe joint together, but it offers larger diameters, massively higher tension limits, and the absolute crucial ability to rotate the pipe to physically drill out hard blockages. The next time you flip a light switch or start your car, think about the immense, complex engineering working miles below the Earth's surface to make that energy possible. We've seen how wells get sick, how engineers meticulously diagnose the symptoms, and the massive mechanical surgeries required to bring them back to life. So whether it's the elegant flexibility of coiled tubing or the brute, rigid force of snubbing, which intervention do you think is the most vital to safeguarding the longevity of our global energy infrastructure? Thanks for joining me on this explainer, and hey, keep asking the big questions.